Okay, thank you. So I will talk a little similar subject, looking at the loading effects in a GPS, except that I will model the loading effects, sorry, not only the hydrology, but also the atmosphere and the ocean, but at the observation level during the processing. The reason for that is that currently it is recommended by IRS and IGS and all the other services not to correct the environmental loading effects except the ocean tides. There are several ways to look at loadings. You can look a posteriori, meaning when you have the solution that was done previously, or at the observation level. And that way, it's the only way to correct the high frequency signal. For example, the air tides, but there are other signal at high frequency. And it will be especially particularly true for other techniques than GPS when you have weekly solution. But even daily solution will have a problem of aliasing. And here, we will investigate the modeling of the full loading effects. By full loading, I mean atmosphere, non-tidal ocean, and hydrology. And I will do that on a global network of more than 100 permanent GPS stations and over a 14-year period. And I will use the Gamit GlobeK software. Just change a little bit of a setup. I use a more recent ocean tide model, so the FEST 2014 version A, not the latest, the B. And here are the other parameters that I used. So a quick explanation on the loading model. The atmosphere is modeled using the ECMWF operational pressure available at 3 hours, meaning I have the S1 and S2 tides. And as it's an operational model, the resolution changes through time, but I ensure the continuity of the time series. The classical way to model the ocean response to atmosphere is the classical inverted barometer, meaning that the ocean will compensate any air pressure variation. Basically, you have no pressure acting at the Earth's surface when you have the IB over the ocean, so you have only the pressure acting on land. And the other model is a dynamic ocean model, barotropic. It's called TUGO-M, or it's also known as MOC2D, that was developed by Laurent Carrière and Florent Liard, and it's forced by ECMWF pressure and winds. So at long period, it will not be IB because of the wind forcing. And for the hydrology, I use two different, let's say, model. One is a pure model, so the GLDAS NOAA model. And I also use GRACE, a different solution, so the solution from the Goddard people. And the degree 1 is added back following the Svensson et al. Method. So, can I have the, no, I don't. Oh, yes, I have here. So, just to show you some plots showing the variability of the different loadings. So here you have the atmosphere, IB, the atmosphere plus ocean. Here the two hydrology model. And you have basically here the vertical annual component from 0 to 4.5 millimeter. You have here the trends between minus 0.2 and 0.2 millimeter per year. And here the high frequency variability with the same scale than the annual. So, of course, when you have a dynamic ocean model, you increase the variability. That's normal, and especially at high frequency. You don't see much trends in the atmosphere. That's normal. And of course, the trends and seasonal will be very, very different when you compare GRACE to models. And here, just a comment also on the variability. Here you have a field that is 3 hourly, here monthly. But it doesn't mean that one has more variability. You have, in fact, more variability in GRACE. I mean, the displacement model from GRACE. By the way, all the loading time series are available in Strasbourg for all these stations. And just here, again, the amplitude of the air tides, the vertical displacement due to air tides, so it's at the millimeter or 2 millimeter level. Of course, it's larger around the equator. And don't forget here for the S2, you have to add the ocean tide too. So here is the global network of stations I use. So pretty global. And in blue, you have the reference station to align to the latest ATRF. And I did only translation and rotation, no scale. That's because you have some regional or continental movement that can go into the scale. So basically, I did 5 GPS solutions with different loading model. The classical solution without modeling any loading. So that's the classical approach. One, I modeled the atmosphere with the IB. The other one with the dynamic ocean model, and the 2 with the full ECMWF plus ocean plus hydrology. And basically, I compare the solution where when I include the loading to the solution without the loading, and I will here mostly focus on the high frequency variability, the annual component, and the linear trend. So basically, I do the station displacement of the solution with the loading minus the solution without loading. And here it is where I only consider the loading from the atmosphere and the ocean. So on the left, you have the ECMWF IB, again, minus the classical. And the other one is ECMWF plus the dynamic ocean. And on top, you have the north component. In the middle, the east. And in vertical, at the bottom, sorry, the vertical component. So if you see red, it means a decrease of the variability. When I take the loading into account, in blue, it means an increase. So clearly, you see for the vertical, almost everywhere a decrease, and it's a little more complex for the horizontal. If I had the hydrology, I have a slightly better result, especially when I use GRACE instead of GLDAS, but there are also still some remaining problems in the horizontal component, mainly the east. I have a reduction almost everywhere for the north. So here it's the same kind of plot, but what I call a relative reduction. So that will be the variance of the solution minus, when I don't correct the load, minus the solution where I include the load divided by the variability of the load. Meaning if I have 100%, it means all the signal that was different in the two solutions is the load. If I find 0, it means I don't improve. And if I find something negative, it means I decrease. So what you can see, I don't reach anywhere 100%. It means that there is another variability in the GPS positioning that does not come from the loading, both horizontal and vertical. So looking at the annual component, again, same kind of plot. It's the annual amplitude of the solution with the load minus the annual amplitude without the load. So again, red means a decrease, blue an increase. So you see mostly for vertical a decrease of the load. And when I add the hydrology, it's even better. One comment I want to make, we hear often that people say that the annual variability in displacement is hydrology. In some places, the atmosphere is even larger than the hydrology if you go to Northern Asia, for example. So if you look at annual, don't try to explain only with hydrology, but the sum of hydrology plus ocean and maybe a little hydrology plus atmosphere and a little bit of ocean. And here are the difference in linear trends. As a reminder, I put the ITRF precision goal of 0.1 millimeter per year. So basically, if you see anything on the map, it means that I'm above 0.1 millimeters. So you see that there is a significant trend. Again, not always, here it's only atmosphere and ocean. There is a significant trend that comes from the loading. If I add the hydrology, it gets, of course, worse. I have larger differences between the solution with the load and without. And to finish, I will show you some detrended GPS time series. So again, on top north, the Middle East, and up for 3 different regions, one in Siberia and real, one in Southern America, Brasilia, and the station of Strasbourg and for, let's say, mid-latitude. And you have in black the solution without the load, in green the solution atmosphere plus ocean plus the hydrology using the GLDAS model, and in red when I replace the hydrology model with grace. And you have the value of the standard deviation indicated as well as the annual, and you see globally we significantly reduce the variability and the annual component. But if you take some other station like Brasilia, there is still some, or Enreal, there's still some seasonal signal even in the vertical. So the conclusion here, we implemented all loading models into the gamete globe K, and it's directly from station 5. There is no grid interpolation. I should send back the routines that I've wrote to the gamete people so people can use it. Clearly, we see a difference between the classical inverted barometer assumption and the dynamic model to go M. It's particularly true for the vertical, but slightly for the horizontal. Anyway, that model is used successfully also for altimetry by the Aviso people. Not exactly the same version of the model, but it's basically the same model. But also for the grace processing, the de-aliasing from the GRGS people in France and also the Goddard people in the US. Adding hydrology, of course, helps reducing the seasonal signal, but also slightly the high frequency variability, and clearly grace is better than GLDAS or any other hydrology model. And one of the reasons that with grace we have all the components, such as the ice sheet, that are not classically in hydrology model, but also there are other components that are usually missing in hydrology model, like surface water, groundwater. And if you want to see the impact of modeling the surface water, you can see Joël Nicolas poster. And there is still a large part of the GPS variability that cannot be explained by loading effects. As the station with problems, when I don't reduce the variability, are close to the ocean, I strongly suspect the tropospheric wet delay to be one of the causes, among others. Okay, thank you.